let's look at another surface area problem, and then I'm going to do a scalar surface integral problem as well. Let's look at the area of the surface. This is problem 47. X equals u squared, y equals uv, z equals 1/2 v squared, with u between 0 and 1 and v between 0 and 2. What does that look like? Well, let's ask the applet first. I put it in as s. I can put it in as s and t because that's how the applet does it. So let's see, 0 to 1 and 0, not 90. Oops, let's make sure. Okay, so let's see what that looks like. Well, it's a little weird. Let's rotate it around. It seems to have some straight lines in it. It seems to maybe have a lot of straight lines in it because there's a lot of perspectives where you can look at it and you could looking along just a line. So let's see. What if we expand the limits a little bit? That often helps, even though that's not what we actually want to integrate over. And if we rotate it around now, it's a cone. And it's a cone that opens not along an axis, whose axis of symmetry is at a 45-degree direction. It looks like in the xz plane. Well, we can get that out of the algebra, in fact. This is not what you need to do absolutely to do the example. But we can see if you take y squared, that's u squared v squared. Hey, that's the same thing as 2xz. And so that's nice. It's a nice, simple quadratic equation. So that should really be a quadric of some sort. And we never did ones where we had a cross term with like xz. But if you remember that we did talk about it a little bit. Z equals 2xy is a 45-degree rotated, whoops, not math mode, rotated version of z equals x squared minus y squared. Those were the two saddle surfaces. In fact, we even saw both of those examples above pretty much. So that suggests that maybe this guy, so maybe that is a rotated version of y squared equals x squared minus z squared. And in fact, you can show that. That's really true. Or in other words, that x squared equals y squared plus z squared. So it's a rotated version of a cone whose axis is along the x direction. And in fact, that's exactly what we were seeing in the applet. Okay, so that's cool. But then, now how do we actually deal with it? Now I actually pre-prepared some stuff because it takes a while to write this stuff down with the cross products and all. So let's see what we have here. Since they're giving us the parametrization, sorry, this isn't working, okay. Since they're giving us the parametrization already, we just calculate our RU and our RV. Let me just bring this down, copy it down below this stuff here. Okay, so 2u, v, 0, 0u, v for the partial derivatives. We put those into the cross product. We get v squared I minus 2u vj plus 2u squared k. And this is usually the tricky thing. This goes all the way back to arc length. We're going to take the square root of something. We're going to take the magnitude. And if that's not a perfect square, or unless we have some nice setup with the integral, it's going to be a problem. But the way they've set this up is particularly nice. You get v to the fourth plus 4u squared v squared plus 4u fourth, and you've got to recognize that 1, 4, 4 pattern. That's a perfect square pattern. This is exactly inside here is v squared plus 2u squared quantity squared. So if you square root it, you just get v squared plus 2u squared. Okay, so that means the area excuse me, is going to be the integral of the limits they've given us in v and u of v squared plus 2u squared dv du. And that's not a particularly hard integral to do. So it's very easy. If you get anything wrong here, you're going to end up with the square root of something that isn't a perfect square, and it's just going to look horrible, and it's going to be impossible probably, or very close to impossible. If you do this thing quite correctly, then you do see that, yeah, okay, it's contrived in the way that arc length and surface area problems often are to be doable. Okay, so now 11 from the next section. Here it's a scalar surface integral problem. We've got the part of the cone, the surface is the part of the cone, z equals x squared plus, z is r basically, z squared is x squared plus y squared, between z equals 1 and z equals 3. Now this is really the double cone because it's all with the squares, it hasn't been square rooted. But that doesn't matter because z is definitely positive for us anyway. So it's a funnel kind of thing, like we were talking about in class. It's part of a cone with the cone point taken out, so stuff could fall out through the hole. So here, I chose not to use the graph parametrization because it would be z equals the square root of x squared plus y squared. That square root makes for a little bit annoying partial derivatives. And so if there's anything annoying about the graph parametrization, we don't have to use it. We used it in the other examples in the other video because it was easy on the algebra. Here, we know we're going to have to go to polar. The whole thing is radially symmetric, and so we might as well go straight to it and just deal with the cross product stuff. This is very much like an example we did in class. It's almost exactly the same surface. X is r cosine theta, y is r sine theta, z equals r. We get the partial derivatives, the velocity vector of the r curves, where r is the variable, cosine theta, sine theta, and 1. R theta is minus r sine theta, r cosine theta, and 0. Put them into the cross product. So there's the setup for the cross product. And we get a little bit of niceness. Well, the 1 and 0 are kind of nice. So in front of the I, we just get sine theta times 0 is 0, minus r cosine theta. There we go. Secret minus sign in front of the j. Cosine theta times 0. I'm sorry, yeah, cosine theta times 0 is 0. 1 times minus r sine theta with a minus. So there's actually 3 minuses. It amounts to a minus here. Times j. And then we get what do we expect from these kinds of calculations, a cosine squared plus sine squared in front of the k. R cosine squared plus, because that's a minus and it's a determinant, r sine squared theta. So that becomes 1. The r factors out, and I get minus cosine theta minus sine theta j plus k. So the magnitude of that guy, magnitude of that vector, is just the r comes out, as any positive scalar would, times the square root of cosine squared theta plus sine squared theta. And so we get again, and then plus 1. And so that's going to be a root 2, equals root 2 times r. Okay. And I talked about in class how that root 2 is a slope factor. The fact that that cone is tilting up at a 45-degree angle gives us a stretching factor of root 2. And then the r is basically the standard polar Jacobian factor of r. So what's the actual integral that we're trying to do? What they're asking us for, is the double integral. Let me get a double integral down here. Over this surface of x squared z squared ds. Oops, I don't really need to go down yet. That's going to be equal to, okay, so we can now set it up. We know, using polar, since r is equal to z here, and z is 1 to 3, so r is going to be 1 to 3, and then theta is going to go 0 to 2 pi. So this is going to be the integral from 0 to 2 pi. That's going to be the theta limits, 1 to 3 in r rather. And now x squared z squared is just r squared cosine squared theta times another r squared, and then times the ds is now root 2 r dr d theta. And that's not too bad. Oops. We're going to get a 2 pi 2 pi from the theta integral. Oh no, we're not actually. So there's a cosine squared theta there. Okay, so it actually breaks up into 2 integrals. Integral, I'll just take it a little further, but then you can finish it yourself. 0 to 2 pi cosine squared theta d theta times 1 to 3 of, looks like r to the 5th dr. And there's a root 2 in front of it. Don't want to forget that. Okay, and those are both fairly quite standard integrals by now.